Okay, fantastic. Okay, guys, let's get started. We're playing a new game now. Input, output, we explained that. And now I'm going to show you a concrete example of input and output. Here's an example of input. You give me a causal structure like this one. There are 4 variables. And then you give me data. Now, look what happened here. The model or the causal structure has 4 variables, X, Y, Z, and U. But if you look at the data, there's only data on X, Y, and Z. You look at every row, that's one example. Normally, we would show repetitions. In this case, we're showing the empirical distribution. That is 11.6% of the data was this example, and so on. 27.4 was this example. Now, what happened here is U is not in the data, so it's actually hidden. The data does not mention it. This is an example input. Now, an example output is you would come and say, I'm interested in this causal effect. I want to fix X to this, and I want to see, the causal effect on Y. You may have another query, a different kind of causal effect, this guy. And then you're going to say, I want a causal effect of Z on X. Now, here's the thing. For this particular example, that is, this particular causal graph and this particular data set, it happens that this is identifiable. And you can, in fact, compute this quantity from this information. And we're going to show you how. But it happens that this is not identifiable, provably. You can never get this quantity or this causal effect from this kind of input, all right? So the bulk of what's going to happen next is determining if something is identifiable or not, and when it is, giving you a formula for doing that. Before we move on, just want to mention a couple of words on notation. If you look in the causality literature, this kind of a network like this, when this guy is hidden, is sometimes drawn like that. So what happened here is there is no U. I just put this dotted edge. We have not seen this in class so far. And this means there's a hidden variable here that causes both of these guys. Now, cuter notation, but there is really something important happening here. Not only did I have this nicer notation, but I even omitted the name U, which implies that I don't even need to know what that variable is, particularly what kind of values it have. And this is suggestive that I may be able to do this game without even making any assumptions on how many values you have, which is pretty remarkable. And that's indeed the case. These results would not need to know what's going on with you as far as how many values it has. One more thing about notation. Typically in this literature, U and U sub I are usually used to denote hidden variables. Okay, so we need to take care of a couple of more issues before we go into these identifiability criteria. One of them is type of data. So we talked about observational data in which variables are either hidden or fully observed, like in this example. U is hidden, but X, Y, and Z are always observed in every example. That's the case we're going to be focusing on. There is another case where you may have also partially observed variables. We're not doing this now, but maybe next time we'll talk about that. So everything here will be a variable is either observed, fully observed, or either hidden. We said observational data. We have not used this term in class before because everything we were looking at observational. Observational data when you're just looking at the world and recording observations. Now, this is in contrast to interventional data because you may go and say, let me go and force Y to be no and see what happens to X and Z in that case. So I intervene in the world. I'm doing experiments. I force the value of a variable and I record the values of the other. In that case, the data will be called interventional. We're not doing this here. We will talk about this next time when we do counterfactual reasoning, where you may have a combination of interventional, observational data, only observational data in this case and of that particular type. The one thing I want to do next is give you an intuition of why something may not be identified. Everything we're going to talk about later is methods for identifiability. You may ask yourself, why is it in some cases something may not be identifiable? And this example is pretty important. It shows you, hopefully in an intuitive way, why it is sometimes impossible to recover the causal effect from data and from a causal structure. And in fact, it will tie to what we talked about, maximum likelihood estimation and the learning methods we discussed earlier. So here's the model we're going to use for this example. Very simple, 3 nodes. All 3 variables are either on or off, right? Binary. So when U is on, Y follows X. When U is on, the value that Y will take is exactly the value that X will take. And when U is on, X is on with some probability, let's call it Q. Now, when U is off, both of these are off. So the CPTs, here they are. They look at the two cases. U is on, then you can see that Y follows X, all of these are 1, and X takes some probability Q. When U is off, then both X and Y are off. Now remember, for Y, when U is off, that means X is irrelevant in that case. Okay, that's what's going on. Now this example was shown carefully so that it has the following behavior. If I come and tell you that both of these guys are off, without telling you what the value of U is, you wouldn't know what caused Y to take that value. So if X and Y are both off, we cannot tell if it was X that turned off Y, or if it was Y that turned both of them off. Now, if U, in this case, was on, you know that it was X that turned off Y, because in that case, Y follows X. But if U was off in that case, then we know that that is what caused both X and Y to take that particular value. So we're trying to create an ambiguity about causation. Now you're going to see it vividly next when we keep going on. Now, if you look at this fully specified model, by the way, this model has only two numbers, Q and P. So if you have Q and P, then this is fully specified, but we're going to keep it in terms of Q and P. But I hope the intuition behind the model is good. Now, if you go and compute the causal effect of X being on Y being on, you're going to find that it's actually P. I'm going to show you the details of the computation here, but you can do them at home. You should be able to follow every step based on what we said earlier. This causal effect is P. Now, here's the point I want to make about this example. If you look at this model and you see what kind of data it will generate, you will find this kind of data. You will see in the data only 3 kind of examples. The first 2 examples are when U is on. Look what is happening here. Y is following X. All right. So if X is true or on, this is on. If this is off, this is off. These are the first 2 cases. The other type of example you see is this. This is when U is off. And as we said, it will cause both of these guys to be off. All right. We're good so far. Now you can do the math and you can see that each one of these cases will appear with a certain kind of probability in the data, right? If you have data in the limit. Now here's the punchline about this example. Look at these 2 guys here. In both of them, X and Y are off, but for different reasons. In this case, Y was off because this caused it, right? It was following X. That's why it's off. But in this example here, the reason why this is off because this guy caused both of these. So these 2 guys are different from a causation point of view. Now, here's the thing. The thing is, if U is hidden, and I'm not showing you these guys, this is the data you will see. You will only see 2 kind of examples, this and that. And these are the corresponding probabilities. What we did here is we added these 2 guys up, so we're getting this. So this is the data you will see, right? So when you see this example, you will not know what happened here. Is it that X prime is causing Y prime, or is it really in the background we have U prime and it caused both of them? And that's the essence of why you cannot figure out causal effect. Because remember, what is causal effect? P. If I show you this data and you get these numbers, you cannot recover P. So for example, if I tell you, I saw this example 14% of the time, and this example 86%. From 14% and 86%, you cannot recover. You can only recover what P multiplied by Q is, but you cannot recover P. So I saw 14% here, 86, right? There's 2 solutions for P and Q. It could be 0.7, 0.2, or 0.2, 0.7. Both of them will give you a product of 0.14. This case will give you a causal effect of 70%. This case will give you a causal effect of 20%. So there is no way from this kind of data to recover the causal effect. Now, interestingly enough, those guys are both maximum likelihood estimates. So if your goal is to estimate parameters for this model based on this kind of data, and you're looking for maximum likelihood estimates, they're not unique. If you are doing associational reasoning, that is, you're only interested in the distribution of X and Y, they're equivalent. Whether you choose this or choose that, no difference. You're always going to get the same answers. But Now that you're doing interventional reasoning, whether you end up choosing this or that makes a difference. You're going to get different answers. All right. So in this case, the causal effect is not identifiable. Okay, this is like, you can look at it at two levels. It's a mathematical example that shows you why it's impossible to recover the causal effect. But I think the bottom line of it is this ambiguity that's happening here is I don't have enough information to figure out what was causing what. I spent a lot of time coming up with this example. You can revisit it later. Okay, guys, let's keep going on. One more topic before we talk about identifiability criteria. Sometimes you can make blank statements about identifiability, depending on the type of the causal graph you have. And I want to show you one particular type of causal graphs for which we know that we can always identify causal effect. This is important in the literature, so you need to know that. So in this example, or in this discussion, we're going to assume that hidden variables are always roots. So people talk about Markovian causal structure or Markovian models, and they're very simple. They say each hidden variable has at most one child. All right, here's an example. These are the root nodes. We're assuming that they're hidden, and these are the only hidden ones, right? Otherwise, these guys are observed. Now, you look at this guy has only one child. This guy has only one child. In this kind of situation, we call this a Markovian model. Sometimes people call this no hidden confounders. Now, in this case, causal effects always identifiable. Any causal effect you ask about the variables that are observed, it's identifiable. The contrary of this is what people call semi-Markovian model. This is when some hidden variables may have more than one child. Here's an example. This is a root, it's hidden, but it has two children. In this kind of model, identifiability depends on the query. And in fact, for this particular guy, this is identifiable, this is not identifiable. All right? So Markovian model, always identifiable. Semi-Markovian depends. And what we're going to be looking at later is ways to tell this from that. So you need to remember Markovian and semi-Markovian. Here, the rest of the discussion. We're going to go back to causal effect rule and view it as an incomplete identifiability criteria. We're going to find that it's pretty weak. And then we're going to go to the famous backdoor criteria, which actually includes this as a special case, you'll see. And this will be more powerful. It will identify more cases or will reveal more cases of identifiability beyond this one. We will briefly mention the Frontdoor, simply just to give you a flavor of what else is out there. And then we will finally end with the do calculus, which is complete. All of these are incomplete. They may come back and say, oh, I couldn't figure it out. As far as I'm concerned, this is not identifiable, but that doesn't mean it's not. This guy is complete. It says not identified, it means it's not. No other method can do it. All right, this is the ultimate guide. And interestingly enough, this is pretty efficient criteria, as you will see later. Now, there are other criteria beyond these, and we can't enumerate all of them. And some of them use even more information than what we talked about, not just the causal graph and data. Some of the recent, in the last couple of years, can use information like context-specific independence, further information about the model to do identifiability. Okay, guys, so let's go and get started with these one by one. First one, causal effect rule. You know what that is. I have a graph. I have X, I have Y, and Z are the parents of X. And here's the formula. It says causal effect equals to this. Just do a summation over the state of the parents. Now, to really apply and compute this quantity, and in which all are association, I need to find these guys out. Now, in this case, I don't have a fully parameterized causal graph. I have data. So to get these quantities, I need to estimate them from the data. And so I need the variables X, Y, and the parents need to be observed. If they are observed in the data, then I'm done. I just estimate these quantities and I plug them into the sum and I got the causal effect, okay? Now, let's look at the example we looked at before, this guy, right? I'm interested in this causal effect of Z on X. Now, according to the causal effect rule, what do I need to know? I need to observe the parents of Z. U is one of them. In fact, it's the only one in this case. So I cannot use this rule because U is not observed. So causal effect rule cannot help me in this case. All right. Now let's look at the other guy. Causal effect of X on Y. Now, if I want to use the causal effect rule for that, I need to know the parents for X. I need to have them in the data observed. Now, Z is observed, but U is not. So again, I cannot use the causal effect rule. So in this case, the causal effect rule could not help me. So if I'm trying to identify or compute these guys, causal effect rule says in both cases, I cannot help you. Because for me to trigger, I need the parents to be observed. In this case, they're not. In both cases, I can't do it. Now, remember what we said earlier. We said this is not identifiable, that's fine. But we said this is identifiable. So this is a case that shows the incompleteness of that guy. This guy couldn't really do this. And now we're going to see the next criteria. The backdoor will actually be able to figure this one out. We'll tell you, yeah, you can do this actually. And it'll give you a formula for it. Okay, so I hope we understand what the game we're up to. The next thing we're going to do is the backdoor criteria. It's pretty famous. You may have heard about it. I need one slide before I go to the backdoor criteria. The one slide is a review of what we did on deseparation, because it does invoke a concept from deseparation. Remember what the central thing in deseparation is you have a path like this in the graph, and the question is this path between X and Y blocked by some variable Z? In our case, when we discussed this before, we talked about convergent valves, divergent valves, sequential valves, ... Causality people make it simpler. They only distinguish between two cases. They talk about these valves, which we call convergent. They refer to these variables as colliders because they are variables on the path in which two edges point into them. And they only make a distinction between colliders and non-colliders. Okay? Now, as you recall from our discussion, for this path to be blocked, what do I need to do? If one of these is not in Z, that path is blocked. Otherwise, if one of the blues are in Z, then it's blocked, okay? That's basically the rule. Just remember that, just a refresher, we should know this from earlier discussion. All right, you guys are ready for the backdoor criteria. We're gonna tell you the backdoor criteria next, and we're gonna take a couple of examples, one simple and one more involved before we get to the other discussions. Here it is. Okay, I'm gonna show you the definition of or the statement of the backdoor criteria. It's gonna, when I put it on the screen, it's gonna look, oh, too much, but it's actually pretty innocent. So here it is, and let's go over it. What's going on here is I do have a causal graph. I'm interested in this causal effect of X on Y. And now I'm interested in finding a set of variables Z that satisfy the backdoor criteria. Now we're gonna go over the two conditions over Z that will earn the name backdoor. But before we do that, if it turns out that you have found a set of variables Z that satisfy these two conditions, and therefore it is called a backdoor, then you can do this. You can express the causal effect this way by summing over the possible instantiations of the backdoor variables and do this. Okay, so the point of finding a backdoor is that I want to evaluate the causal effect using this formula. As long as this is a backdoor, this works. All right. Now, in practice, of course, this criteria helps you if the backdoor ends up being observed, right? Because then you can estimate these quantities from the data. Okay, but let's look at the two conditions that allow something to be a backdoor. The first condition is simple. It says no node in Z can be a descendant of X. X is the guy we're intervening over. Okay, you cannot include descendants of X and Z. One. The second is Z must block every path between X and Y. But there is a qualifier. I'm not interested in every path between X and Y. I'm only interested in these that contain an arrow pointing into X. So there's many paths between X and Y. I only care about the ones that have an edge going into X. I want them all to be blocked by Z. And moreover, I want Z not to contain any descendant of X. If these two conditions are met, I will declare Z a backdoor, and then I can use it to invoke this formula. So if X, Y, and the backdoor are observed, I'm done. And it is identifiable with the causal effect. All right? Okay, let's take a concrete example. First, simple one. And this is our friend, the one we talked about earlier. Okay, remember, we had two queries on this guy. One we said is identifiable, the other is not. Let's see how the backdoor will do on this. All right? Now, what am I interested in this guy and in that guy? And remember, causal effect rule did not help us with either. Let's take the first guy. You tell me, I need to find a backdoor. So I'm talking about X and Y. So I need paths between them that point into X. And I want to make sure that they're blocked by something. in this case, I want it to be observed, right? How many paths? Tell me, how many paths between X and Y that we need to check? How many? Can people type a number there? People are saying 2. Okay, let's see. This is one of them, correct? This is one of them. And this is another, right? So there's 2 of them. Good. Now, it turns out that this variable Z blocks both of them. Actually, let's see them here. This is one of them. And Z is not a collider, it's a blue guy. So it will block it. And look here, same story. Z is not a collider. If I observe it, then I can block this. So actually Z is a backdoor in this case. It blocks both of these guys. And Z is observed, I'm done. I can identify this guy and the backdoor gives me the formula to do it. We'll be doing a summation over that particular variable. All right. So here's a situation where the causal effect rule said, I can do it. And the backdoor said, I can do it. All right. Now, if you look at the other guy, now X and Z, how many paths do we have to look at here? 1, exactly. And that's this path. There is no way to block this without knowing this guy. But this guy is hidden. I can't do it. So there is no backdoor in this case in that sense. And because this path cannot be blocked by observed variables. So I'm not able to use the backdoor criteria in this case. But that shouldn't be surprising because provably this is not identifiable. So not only the backdoor, but any other criteria should be able to say yes on that. All right. So an example where we got more out of the backdoor than we got out of the causal effect rule. And later we'll see a situation where backdoor cannot help us and say, oh, I can do this. But the do calculus will say, no, I can do it. All right. Okay, let's do one more example on backdoors, which is more involved. We can look at this bigger example. And we're interested in the causal effect of X on Y. And in this case, we're going to assume everything is observable. So everything can be a legitimate variable for a backdoor. All right, so all variables are observed, no hidden variables. Okay, so backdoors. What is a backdoor in this case? Do we have a backdoor? Again, for the causal effect of X on Y. Now, again, what we need to do is look at every possible path between X and Y in which X is pointed to. How many paths do we need to check? Those are paths between X and Y that point into X. And we call these the backdoor paths. Someone is saying 3. Someone is saying 5 and 4. Okay, I'm getting more 4s than anything else. And that's actually the correct number. So let's enumerate them. Here's one. This is good. It's between X and Y and it does point into X. So it's something I need to check. Now, I can block it by Z, right? Z will block this one, correct? So let's say Z is now the candidate for our backdoor. We'll start with that. Let's check the other path. This is another path between X and Y. Here it is. And it does point into X. So that's a guy we need to check. Is this also blocked by Z? Yes or no? Is this blocked by Z? Yes. So we're still good. We looked at 2 of them and it looks like our candidate backdoor being the variable Z is good. It blocked both. Here's the third one. I can go this way between them. And again, still this points into X. So this is a guy I'm going to check. What about Z? Will Z block that guy? Yes or no? Looking at the chat. So people are saying yes. Okay, wow, we're lucking out. So Z so far blocked 3 of the paths we need to worry about. We still have one more. This guy. This is one other way to go between the 2 guys. Now, will Z block this? No. So Z is a collider on this path. It was not a collider on this. It was not a collider here. It was not a collider it is. Now we're in trouble. What do we do? Any suggestions? What do we do in this case? So Z cannot be a back. Any suggestion? Okay, someone saying add E to it. So if we add E, E will block this path. And all of these paths will continue to be blocked by E and Z. Good. That's a candidate backdoor. We found a backdoor. E and Z. Are there other backdoors? Did I need really E? Could I have observed A instead? Okay. Someone's saying, okay, Nadab, good. Saying do A and Z. Indeed, that's one candidate. This is another candidate. Actually, I can have all if I want. A, E, and Z. They will satisfy the criteria of a backdoor. And of course, 1 and 2 would be preferred because those would be smaller. Now, remember, when we're doing the backdoor, we needed to look at the paths that between X and Y that point to X. And the backdoor had to block the path, but also could not include variables that are descendants of X. So this was implicit in what we were saying. But good, guys, you're expert on backdoor. All right? Okay, so here's what we're going to do next. We're going to go ahead and show you an example where the backdoor criteria fails, in the sense that it would look at an example, it says, and we can't use it on that example, even though using other criteria, that example will be doable. Okay, before I show you that example, one word about another criteria called Frontdoor. We're not going to discuss this in detail. The only thing I want to tell you about this is, just like the backdoor criteria, it says a set of variables satisfy the front door if ... I'm not listing ... because they're a little bit more involved than the backdoor, and we don't need. You can look them up. But the point is, if indeed you find a set of variables, Z, that satisfy the front door criteria, then this says it is identifiable and it gives you a formula. The main point I wanted to tell you is the formula is different than the one for the backdoor. This is the formula, but it still have the same form. On this side, I have interventional probability causal effect, and on this side, all associational quantities, all right? That involve, in this case, X, Y, and Z, except Z now is a different set of variables called the front door, satisfy different criteria. The point here is, the reason I wanted to include this, even though I don't want to discuss the details, is up until this point, whether it was the causal effects or the backdoor, the formula always looked the same. No, it doesn't have to. And in fact, when we go to the do calculus, we'll produce even different formulas than either this or the one we've seen before. The main point about the formula produced by identifiability criteria is that it's all in terms of associational quantities. All right, I hope this point is clear. You can look up the Frontdoor criteria. Let's go ahead and look at an example where backdoor cannot help us. And then we will see that the complete criteria of do calculus will be able to help us in that case. Are you guys ready? We have 2 more topics to cover. Ready? In the box, chat box, anybody ready? I hope still the audio is there. Okay, at least Vishnu is ready. Okay, let's do it. This is the example that we're going to look at. Incompleteness of the backdoor criteria. This is actually a fun example. And let me once more give credit to you that a lot of these fun examples are from him and his books. I'm going to show you 2 examples that are variations on each other. In the first one, in both of them, backdoor says I can do it. And in one case, backdoor is right. Not only it cannot do it, nobody can do it. But in the other case, the other variation on this guy, backdoor will also say I can do it, but it can be done. So here's the first version. Smoking, cancer, and genotype. So the idea is, yes, smoking causes cancer, but it's possible that there is a genotype that causes both of them. All right, this is the example. And we're interested in the causal effect of smoking on cancer, right? You guys know this guy right now. Okay, so backdoor, can you help us here? Remember, this is hidden, these are to observe. So is there a backdoor? This would be X, this would be our Y. And backdoor would say, let's look at the paths, backdoor paths, there's this guy. That's the only one, right? And the only way to block it is to observe this guy. And we cannot observe this guy because it's hidden. So there's no backdoor in this case. So we can't invoke the formula. And backdoor says, I can do it. And indeed, this is not identifiable. You can't do it here, not just by the backdoor, nothing else can do it. Now, let's look at the variation on this guy. So now we have another variable. So we're measuring the amount of tar, right? That is caused by smoking, and this could cause cancer. So we have 3 observed variables, this, and that. This is still hidden. Now, I'm still interested in this quantity. Can you find a backdoor in this case? How many paths do we have to check in this case? People are saying 1. It's just this guy. Same story. And the only way I can block this, if I observe that, I can't observe that there's no backdoor. So backdoor criteria cannot help us in this case. But guess what? This example is identifiable. In this particular model, I can indeed, given observations on these 3 guys, data on these 3 guys, I can in fact do that. Backdoor cannot help me. Now we're going to end with the do calculus, and we'll see that the do calculus can actually do this example, and it will give me a formula for it that expresses this quantity in terms of associational quantities over only these 3 variables. All right, the do calculus is going to be our last topic. Now, before I show you what the do calculus is, I have to just make a remark. It is different from what we've seen. It is based on transformational rules. What does that mean? It will take the causal effect, that is probability of y given do x, and then tries to rewrite it. And it has 3 rewrite rules. We will see them. And the idea is, I want to keep applying these rewrite rules until I finally get an expression that involves only associational quantities, no interventional quantities. Okay? And the 3 rewrite rules try to do that. So the way it works is you take your interventional probability and start applying these rules. And then one of 2 things can happen. Either you're going to get an expression that is only associational at level 1, in which you declare success and you say the do calculus says this guy is identifiable and here's your formula. Or you will not be able to do that, in which case the do calculus says no. And then in that case, we trust it and say not identifiable, and nobody dares to say that it's identifiable because provably it's not. 2 things I need to say before we start. This process, even though it looks, when I show you an example, it looks a little bit complicated, there is an efficient algorithm for it, okay? And we're not gonna do it in details because every derivation is different and it's like doing proofs, right? But hopefully with what we'll say in the next 2-3 slides, you'll get a very good idea what do calculus is. I'm gonna show you now the 3 rewrite rules of the do calculus. And they refer to the variables x, y, z, sets of variables that are disjoint. So here's the first one, this guy. Okay, first, look at it. Digest it for 5 seconds before we talk about it. It's very innocent. And you should be able to completely read it except for one component. It is titled Ignoring Observations. And what it says, you can rewrite this as that if something is the case. Ignore the case for now. Let's look at what happened here. I'm looking at y given do x, z, and w. And look what happened. I dropped z. I said, you can take this guy and replace it with this. Drop z. If the following happens. Now, what is this? You know this, deseparation. If y and z are deseparated by x, w. The only thing that's new here for us is the deseparation is not in the causal graph, but in a modified version of it. I'll tell you what this notation means. For now, all you need to know is not G, it's an alteration of G. Okay? But otherwise, you would know how to apply this guy because you know how deseparation works. All right? This is ignoring observation. Let's look at the second rewrite rule, which is going to be very similar, okay, in terms of form. And it's called action observation exchange. Look what happened. I got this guy, and then I said replace it with that. You can replace it with that, or of course the other way around, if something is the case. Now, what happened here? Do z here, and then z. So I'm saying whether you intervene to set z or whether you observe z, same thing. You're going to get the same thing. If this is the case. What is the case? Same story. Deseparation between y and z by these guys, but in this graph. Okay, I say, oh, what about this? What about that? We'll talk about this in just a second. All right. The third rule, anybody wants to guess what it's going to be called? Okay, ignoring observations, action observation, exchange. Make a guess of what, do induction. What's the last one is going to be called? Ignoring actions. Yes. Okay, good. So what happened here is do x, do z, and then I ignored this guy. And I said just this. These are equal if, again, some deseparation holds in this guy. Now, this, and that are just all modifications of G. I'll explain that in a second. But look, nice, easy forms have intuitive meaning. And let's explain what this guy is. This is the graph G after removing edges pointing to X. So X overline. Take G, remove every edge that points into the variables X, and that's your guy. So in this case, when I'm checking deseparation, I want to check it in that kind of a guy. Underline graph G after removing edges outgoing from variables G. All right. So then what is this guy? That is, you take G, you remove edges pointing into X, and you remove edges outgoing from Z. That would be this guy. Okay, so it's pretty simple. There's only one thing left that I'm not spelling out. This guy here says, okay, we know what this is. Edges incoming into X. Now this says edges incoming into what is that creature? Z parenthesis W. That basically means not all variables Z, but only those variables Z that do not have ancestors in W, okay? In this graph. You can look up this in the Causality book, but it's just another variation of these guys. I didn't spell it out here because a little bit hairier with these guys, but I hope you guys see what's going on, okay? Pretty simple, pretty intuitive. The only thing that you should be worried about is like, when do I apply these? Because I'm going to show you an example next. We're not going to go over it in details, but you just have to see the style of using the do calculus for showing that something is identifiable. And what you'll see is like a proof. You start with a causal effect and start doing steps. And you justify each step either by application of probability axiom or by one of these rules. And just like any proof, you're going to tell me, when do I apply this? I mean, how do I do it? There's no systematic way of doing it by hand. And that you shouldn't worry about, because there is an automated way of applying these rules, either to come back and say, yes, they did the job, or they cannot do the job. So we're going to end with a couple of slides. The next slide is an example application of the do calculus on this example that we've seen. Remember, we looked at this example. We wanted to see if this is identifiable, this particular causal effect. And Backdoor said, I can't help you. And now we're going to see that the do calculus will say, no, this is identifiable, and it will give us a formula for it, an associational formula for it. So next, I'm going to dump a derivation on you. Suddenly, the screen is going to get very busy with equations. Don't worry. And here it is. Let's stare at this a little bit. Understand the structure of what's going on here. I'm starting with this guy, and my goal is to end with this guy. The difference is, this is interventional. Look here. No do. Everything is associational. That's my target. If I get this equal to that, then what? Because in this case, S and T and C are all observable, I can estimate these probabilities from data. I plug them in here, and boom, I evaluated the causal effect, and the causal effect is identifiable. Okay? And look at the formula here. Its form is different from what we've seen in the other front door or back door and so on. And for other derivations or for other examples, you may even get other formulas in terms of structure. Now, every step in this derivation, as you see, was either due to a probability property or due to one of the three rules. And I'm going to show them to you on the side. And when we distribute the slides, you can track them by hand and check them. But before I do that, let's see, look what happened here. This was simply an application of a probability axiom. I did basically case analysis over T. I got this. But let's look at what happened here between this and that. This quantity remained. What happened to this quantity? I had T here, observation, and then I ended up having do T here. All right, so I did an action observation exchange. And in fact, this was by rule 2. And the condition that triggered rule 2 was on this modified graph. Remember, all of the conditions of the rules are on modified graphs. And these are subgraphs of the original one because we're removing edges from the original guy. So at home, you can go check this, and you'll see that this is the guy you need to check the condition on. So that triggered the rule 2, and I replaced T by do T. Now let's see what happens between this guy and that guy. This do S became S. I did another exchange. So this would be rule 2 again, right? And in this case, it was rule 2, but it was on a different graph because different variables were involved. And then what happened here? I dropped do S. So this is ignoring actions. When I went from this to that, there is a missing parentheses here. So I dropped S, so that would be rule 3. So rule 3 triggered here and said, you can drop this guy. And then another application of probability axiom, and then another rule 2 and another rule 3, and then I have that, okay? So now that I got this guy, the causal effect is identifiable, and I gave you a formula of how to evaluate it based on your data. Once more, there is a polytime algorithm for the do calculus that either terminates with a yes or with a no answer. So this is efficient. And the other important thing about the do calculus, it is complete. If it comes back with a no answer, then you know the quantity or the causal effect is not identifiable. And that basically wraps up the discussion on this. So in summary, in this part 2, we defined a new game. The game is I give you a causal graph and some data that doesn't cover every variable in the causal graph. And then I give you a causal effect and I say, is it identifiable? Am I be able to compute its quantity, what's very uniquely from the data? And we went through a succession of methods for doing this, weaker ones, stronger ones, all the way to this most powerful criteria, which is the Ducat cross. All right, so I'll just wrap up with one slide, and then we can see if we need to answer any more questions. The concluding remarks is that when you bring in the subject of causality, you bring in these three levels of what people call the causal hierarchy: associational, interventional, and counterfactual. Again, everything we talked about so far is associational, but the machinery we built for that is usable in level 2 and 3. So, and level 2 is what we talked about today, which is interventional reasoning. Next time we'll talk about counterfactual reasoning. The key thing here is a distribution is not enough for layers 2 and 3. We need a causal graph. That's additional information. Another way to state that, I keep saying it here because you hear that a lot, data is not enough for layers 2 and 3 because data does not have enough information to answer 2 and 3. The last remark, and I want to put it here because I want to introduce another term which we didn't use in the lecture, but it's commonly used in the literature, is that cross-layer inference is sometimes feasible. Now, cross-layer inference is the term I want to introduce, but it refers to this idea of using quantities at one level to answer questions at the other level, and that's what we've been doing in the second part. You give me a causal graph plus some partial data, and then I go find all of these associational quantities that if you put them together, you obtain a quantity that is interventional. Another example of cross-layer inference is if you have associational and interventional quantities, you put them together, you end up computing counterfactual query. So you use quantities from layers to do something at the next layer under some conditions. People refer to this as cross-layer inference, and that's what we did in the second part. We are done for today, and I also wish to thank Scott, who helped with some of the examples, our TA, doing his PhD on causality with the pearls. Thank you, Scott. And we'll leave it at that. So I'll be happy to take any questions.